Good morning. We're going to talk about antiderivatives, Chapter 4, Section 8. And an antiderivative is the reverse, you might say, the inverse of a derivative. It is, in fact, where a derivative has come from. If we have something like, and let's make it simple, so let's talk about having 2x. If 2x is a derivative, we recognize that it came from x squared. Now, notice the notation. The antecedent, or what came before, gets the capital letter, and the derivative that it produces gets the little letter. But we're going to be working in reverse here. We're going to be taking the derivative and we're going to go backwards. We're going to find its antiderivative, where it came from. This is the inverse operation. Now, when we take the inverse, this first theorem is talking about the most general antiderivative, and notice that it's adding a c, or a constant, onto the end of it. And there's a great little diagram in this section, and it's labeled Figure 1. And Figure 1 is talking about, well, the antiderivative, if you will, and it's sketched here in red ink, and it's the antiderivative of x squared. In other words, if you took x cubed over 3 and found its derivative, wouldn't you have 3x squared over 3? And of course the 3's would cancel, right? And that's why we're calling this guy x squared. So x squared is little f. Big F, you might say in this context, is x cubed over 3. And we'd want to add the plus c because we don't know which of these curves brought about the derivative x squared. That is, it could have been any one of these 6. In fact, it could have been any one of an infinite number of curves. Notice that these curves are all just stacked one over another. And if we take the derivative of any one of them, when it comes to taking the derivative of the constant on the end, that's 0. And so in each and every case, when we take the derivative, we get x squared. And if we try to go backwards, we cannot account for or pick up for this so-called constant. So we recognize that it's there by just adding it on the end and saying, you know, we don't know which curve it is, but this whole family of curves is related. For instance, if we go out 1 unit, and I don't know where 1 is, but it doesn't matter which curve we're on. If we're talking about its direction or derivative, notice that each one is pointed in the exact same direction at that moment. Doesn't matter which one we're on, they're all going the same way when it comes to being out 1 unit. They all have a slope of approximately or exactly 1. Well, let's look at one more thing. So if you turn the page in the book, you'll notice what's called a table of antidifferentiation formulas. That word is a mouthful. But the table, simply put, is a way for us to work with finding these antiderivatives, and that's what we'll use to start. Some of them will become so common to us that we'll no longer need to look at the table. The opening two are just reminders to us that if there's a constant in front of a function, we don't have to worry about it. We just include it at the end with the antiderivative of f. And if we've got a sum of functions, well, the antiderivative is the sum of the antiderivatives. And here's what you might call the reverse power rule. You know, the power rule said if we wanted the derivative of x to the n, we'd take n times x and raise it to the n minus 1. Now the inverse of that is to add and divide. So for instance, when our function was x squared, which we were just looking at, if we wanted the antiderivative, we'd say, well, using this rule, right? Using this rule, we'd say add 1 to the power and divide now by that number. So x cubed over 3. And then if we wanted to make it general, we'd add the plus c. So we're going to refer back to this table several times when we work through some examples. So let's look at some examples. And the first two are using this reverse power rule. And over on the right side here, I've gone and reproduced that little portion of the table. And this one says, geez, if we want to find the antiderivative of 8 times 9 to the x, it would be just this simple. The 8 would remain. We would add 1 to the power and then divide by that number. We get to do it again here. The negative 3 remains. We add 1 to the power. We divide by that power. We get to do it again. And what do? Well, we add 1, divide by that number. And the instructions ask for the most general, so the most general means we'll put the c on the end. Think about it. If we reduce this, we get 4/5 x to the 10th minus 3/7 x to the 7th plus 3 x to the 4th plus c. To check it, we might simply take and find the derivative. If we find the derivative of big F, don't we get 10 times 4/5? And 4/5 of 10 is 8. 8x to the 9th. Oh, there it is. 7 times negative 3/7, wouldn't that be a negative 3x to the 6th? 4 times 3, wouldn't that be 12? 12x cubed. And if we took the derivative of any constant, wouldn't we get 0? And isn't it understood that there's a 0 on the end here? Now, some of these problems require a little housekeeping before we get started, and 4 is an example of such a problem. So it might be best for us to say, well, this is x times, and if we expand 2 minus x squared, isn't that 2 minus x times 2 minus x? And if we FOIL 2 minus x times 2 minus x, won't we get x times 4? Outsides and insides will yield negative 2x and negative 2x. And last times last will give us that x squared. So if we pull it all together, won't we get x times x squared, or x cubed? We've got negative 4x times another x is a negative 4x squared. And then we got x times 4, which is 4x. So I changed up the order a little bit, but I was anticipating keeping it in a conventional order. So now if I want to find big F, what am I going to do here? Well, I'm going to use this reverse power rule that we have just above here. Let's see if I can bring that into view a little bit. And remember what that says is if we're going to work with this, what we want to do is have x to the 4th over 4 minus 4 times, and now apply it again, x cubed over 3. One more time, plus 4 times, won't it be x squared over 2? And finally, a plus c. Now, this can be reduced or written this way, 1/4 x to the 4th minus 4/3 x cubed. 4 over 2 leaves us with exactly a plus 2x squared plus c. And again, you can check it on the end. Take 4 times a quarter and you get 1x cubed. There it is. 3 times negative 4/3 would give us a negative 4x squared. 2 times 2 would give us 4x to the 1st. And the derivative of any c would be 0, right? So we've checked it, and we've checked it. We're sure of it. Now, let's look elsewhere in the table. And number 12 gives us a couple of different things to look at. The antiderivative of e to the x is, as you might expect, e to the x. If the derivative of e to the x is e to the x, I think it makes sense that its reverse, the antiderivative of e to the x, must be e to the x. And this one, although it looks a little strange, the antiderivative of secant squared must be tangent x. Why? The derivative of tan x is sec squared x. So we're going to move backwards with this one with number 12. And f of x, big F of x, the father, if you will, the antecedent of little f of x, isn't that going to be 3e to the x? Why? Because the derivative of 3e to the x is 3e to the x. We continue. The 7 just remains in the antiderivative, that scalar. But now the antiderivative of sec squared x is tan x. And don't forget your c. In order to check it, go term by term and take the derivative. The derivative of 3e to the x, yep, indeed, that's 3e to the x. The derivative of 7 tan x would be 7 sec squared x, and the derivative of any constant would be 0. So we've done it and we've checked it. Let's take a look at yet another example. Now, 18 is a little different because it provides us with what I call some additional information, which we'll use at the end. So take a look at it, and before you do, consider the fact that we have 4x, or f of x equals 4, isn't it x to the 0? We never write that, but you know, x to the 0 is 1, and 4 times 1 is 4, right? So we've got 4x to the 0 minus 3 times, and isn't what's described by 1 minus x squared to the negative 1, isn't that the same thing as 1 over 1 plus x squared? And I do all that because now the antiderivative, won't that be 4x to the 1st over 1 minus 3 times, and now right to the table, the antiderivative of this quantity is the inverse tangent of x. And that's because the derivative of inverse tangent is, in fact, 1 over 1 plus x squared. Check your yellow or your peach sheet if you aren't sure of that. You'll find it there. Finally, don't forget about our plus c. But now we are going to use this additional information. Notice that we know that if f is 1, if we put 1 in for x, and we get 4 minus 3 times the inverse tangent of 1 plus the c, it's supposed to equal 0. Well, the inverse tangent of 1 is, in fact, pi over 4. Again, you can get that from your calculator or your table. The inverse tangent of 1 means what? Tangent was 1, and it was the tangent of 45 degrees, or pi over 4 had a tangent of 1. So we're working this problem backwards, and plus c equals 0. Doesn't that mean that c, if I leave that on the left side and take that negative 3 pi over 4 over to the right side, it'll become 3 pi over 4. And if I take that 4 over to the right side, won't it become a minus 4? So notice that I've recovered c. So my final answer for this problem, my big F, this time doesn't have to have the plus c. It can be written this way: f of x, the antiderivative is 4 minus 3/4 pi, or 3 pi over 4. I'll write it that way. I just screwed up. Let me take that away. I'm particularizing it, and I'm supposed to be generalizing the antiderivative. So starting again, f of x equals, and I'm supposed to be looking back on this line, isn't it going to be 4x minus 3 inverse tan x? But now it's not necessary for me to write plus c, because I know what c is. C is 3 pi over 4 minus 4. So that is the particular, not the general now. We had enough information to recover what we call the particular. And we'll make that distinction. This is a particular antiderivative. If it's got the plus c on the end, it's called general. If it's got c filled in, it's called particular. I think I've got one more here. Let's take a look. I do. And this time we're changing the context a little bit. Rather than saying little f and big F, we're saying we've got the derivative. Let's go back to the function. Let's take a step back. Where did it come from? And this problem offers us the opportunity to use that reverse power rule again. I've got it from the table over on the right here. And remember how that works. We put down the 8, that is that constant, and then we say, okay, add 1 to the exponent, divide by that number. Do it again. We've got 12 times, well, won't it be x squared over 2? We've got 3, and won't it become x to the first over 1? I really don't have to write that, but just for completeness sake. And then I'll put the plus c. Now that's the general antiderivative. I can certainly clean it up a little bit. Isn't it 2x to the fourth plus 6x squared plus 3x plus my c? And I can check it by simply taking the derivative, and 4 times 2 is 8x cubed. Next term, 12x to the first. Next term, 3, and the last term take the derivative 0. I've checked it. Now once again, I've got some information here about what is supposed to happen if I put 1 in. If I put 1 in, won't I get 2 times 1, or 2? Won't I get 6 times 1, or 6? Won't I get 3 times 1, or 3? Won't I have my plus c? And all of that, when I put 1 in, what's supposed to come out is 6. Well, I've got more than 6 here on this side, right? I've got 5 more than 6. So does it make sense to you that c has to be -5? We could certainly do that by pulling everything over to the other side and isolating c, but I just wanted you to see that, we already had 6 over here on this left side, so we don't need anything more. And to get rid of 2 and 3, c must be, this guy must be -5. So now we've recovered what c is for the particular antiderivative. So we would say f of x has to be, and this is particular, not general now, 2x to the 4th plus 6x squared, or not a room down here, 6x squared, plus 3x, not a plus c now, but rather -5, because I'm going to use this guy, right? So I think that's all we need to do to get started, and I'm going to make an assignment now on page 321, and I'm going to ask you to do 1 to 23, the odds, and we'll be ready to talk about those in class tomorrow. Have a good holiday, and we'll see you tomorrow. Take care.